All right, folks, it's Bass Action back in action here. In this video, we're going to look at finding missing values in similar triangles using proportional parts. And then at the bottom, we're going to do a special theorem that's often forgotten. So you'll want to pay special attention when we get to that. All right, in our previous lessons, we've talked about the fact that if two triangles are similar, then their corresponding sides would be similar, okay? They would have that scale factor. So number one is just a basic corresponding sides. That one's not going to be anything unique, other than I want to call your attention to and remind you to always use a similarity statement if one has been provided for you. When we look, let's say, at the triangle here on the right, we can see that the 5, the VW, from our similarity statement should correspond with the ZW in the triangle on the left. So when we set up this proportion, I'm going to say 6.4 over 5. Then it's easier to understand and just immediately see that the 12 corresponds with the x. So 12 over x. Now we can just cross multiply this. We'll get a quick 6.4x equals a 60. We've talked already that we're going to have a lot of weird answers. This one is a terminating decimal, 9.375. And if you were asked to round it to tenths, you would just round that to 9.4. Now, if the corresponding sides are proportional, then all of those other special segments that we studied in Chapter 5 are going to be proportional, meaning the corresponding altitudes will be proportional. So we can look at and see that we're going to have an 11 over a 33, matching up those corresponding parts, so 11 over 33. Being consistent, starting with the triangle on the left again, then we'll do x over 21. Again, I always like to remind you that it is good to do a little reducing. It will help you avoid some errors with your cross multiplying. So we're going to have a 3x equals a 21 and an x equals 7. Pretty simple. If the corresponding altitudes are proportional, then the corresponding angle bisectors will be proportional. Again, we can just do, let's say, a 135 over a 54. Matching up the two corresponding angle bisectors. Then we can match up the x over the 72. This left-hand side does reduce. You probably don't see it right off the bat, but I would encourage you to pause the video and recognize that it does actually reduce to a 5 over a 2. We'll cross multiply. We'll get a 2x equals a 360. So then x equals a nice 180. Let's go back up here to the top on the right-hand side. We've seen sides be proportional, altitudes be proportional, angle bisectors be proportional, and of course then perpendicular bisectors will be proportional. Now on this one, notice that I didn't give you any triangles, so it might be very helpful to just draw two quick little triangles. They're called BUG. We'll name them in the same order. And the other one is FLY. So we're going to start in the same place. So the parts will match up, kind of lining up. So the left here and the left here and the right and the right and the bottom and the bottom. That's just going to make things a little bit easier for us and feel more confident in our similarity statement and in our proportion. Marking the parts that we have, we're given that BG is 15. We're given that the perpendicular bisector of BU, which means we're talking basically about something that's going to come to this side, that perpendicular bisector is going to be 27. FY is 10. And then we want to find the perpendicular bisector of FL. So again, it'll be a segment that's going to come in right there. But what that lets us understand is that confidently these two are corresponding and these two are corresponding. So when we go to set up that proportion, I'm going to say 15 over a 10. And then I want the perpendicular bisector from triangle BUG. That was the 27. So I'm going to put that one on the top and I'll put my x on the bottom there. This one's a little bit easier to reduce here on the left to a nice 3 over 2. We can cross multiply 3x equals 54. If you don't have a calculator, you could leave your answer as 54 over 3 now. And if you do have a calculator, or you're doing this, for example, in Canvas, and you needed a decimal, you would type in that decimal. This one does, in fact, actually reduce. Sorry, I wasn't paying much attention there. It is actually going to come down to a nice 18. It's kind of unusual in this chapter. I get pretty accustomed to them not reducing. On our next one, now the medians are going to be proportional. Same story throughout this video. All the corresponding special segments will be in the same ratio as those original sides were. So this one's going to just jump into a 12 over an 8. Go back to the triangle on the left, and we're going to do a 24 over an x. Again, I like to always do a little bit of reducing. This one's also going to reduce to a nice 3 over 2. It's a pretty common one that we like to use. 3x is going to equal 48. This one will come down to a nice whole number of 16. This one, we saw this when we were talking about our similar figures on the front of your foldable. If the corresponding sides are proportional and all of their individual segment lengths are and special segments are proportional, then the perimeters themselves are proportional. So we can find a perimeter by just using one pair of sides and a perimeter and not have to find all the missing parts. Now, these two triangles have been drawn to ensure that you use that similarity statement. I'm going to keep coming back to that, guys, and really emphasizing it. When we look at triangle FUN, the only segment that I'm given is 14. And that segment, UN, is going to correspond to HS. We want to make sure that we get those matched up correctly. There's a temptation to just look at the picture and match the 14 to the 24, and it doesn't. These are the similar parts. Then it also gives us that the perimeter of triangle FUN is 43.5. So this perimeter is 43.5. We need the perimeter of the other. So I'm going to say 28 over 14, left to the right. I don't know the perimeter on the left, but I do know the perimeter on the right, 43.5. Then I can go ahead and reduce this left side to a 2 over 1. I can cross multiply, and now I'm just going to immediately get my answer of x equals 87. Now, this bottom theorem, okay, this angle bisector theorem, opposite side theorem, is a pretty important theorem, and students forget this one a lot. The major difference between this theorem and these figures and the figures that you see up above and all the examples up above is, notice that on problem number 1 and problem number 2 down here, I only have a single triangle that's been given to me. I have one single image with an angle bisector, as opposed to directly above it, I have also working with angle bisectors, but I have two separate, completely separate similar triangles with their own angle bisectors drawn in. That's a major clue that you want to use this new theorem when you have a single image and one angle bisector. So let's take a look at how this one's going to work. The way the theorem works is it says that if an angle in a triangle is bisected, it will divide the third side, meaning the side that it's intersecting. So if the angle is bisected, this third side is divided proportionally, meaning the ratio of these two parts is the same as the ratio of the two sides in the original image. So this ratio is the same as this ratio. So when I go to set this up, what I can do is I can say, if I'm trying to, let's say, find x, I have many options. I could say 11 to 14 is equal to x over 17, or you could actually do the left side over the left part and the right side over the right part. There's lots of ways that this can get set up. So I'm going to go with that one. I'm going to say left side over left part is right side over right part. I'm going to cross multiply. I'm going to get a 14x equals a 187. This one's not going to be a nice terminating decimal, so I'm going to round it to tenths and get a 13.4. On the last one here, same deal. I have a single triangle with a single angle bisector drawn in. So I know that the ratio of the two parts is the same as the ratio of the sides, but this time I've given you the entire side and I want AD. So I'm going to put an AD, an X on AD, and then I'm going to put an expression for DC, and I'm going to write it as a 17 minus X. Now I can do left side over left part, right side over right part. So I can say 11 over X equals 14 over 17 minus X, cross multiply 14X, 187 minus 11X, kick the 11X to the other side, we're going to get a 25X equals 187, so X is approximately, oh, this one's not even an approximately, I just realized, let's erase that. This one is actually going to be equals a 7.48. All right, so when you get to class, we are going to do more examples with this, and then we're going to start combining this with all of the other things that we have learned in the chapter so far.